Hello everyone. Today we are going to dive into the power of lenses. Lenses, as you know, are optical devices that bend light to form images. You might have already used them in glasses, magnifying glasses, or even cameras. But what exactly do we mean when we say a lens has power? Let's break it down. The power of a lens is its ability to bend light to either converge or diverge it. A converging lens, like the one you find in magnifying glasses, brings light rays together, while a diverging lens, like in glasses for nearsightedness, spreads light rays apart. Now, how do we quantify this power? The power P of a lens is defined as the reciprocal of its focal length f. Mathematically, that's written as power equals 1 divided by focal length, where power P is in diopters and focal length f is in meters. It's pretty simple. The smaller the focal length, the greater the power of the lens. For example, if a lens has a focal length of just 1 meter, it has a power of 1 diopter. The unit of power is called the diopter, symbolized as D. So, the higher the value of power, the stronger the lens. Finally, lenses with a positive focal length are called converging lenses, while those with a negative focal length are diverging lenses. So, the next time you use a magnifying glass or look through glasses, remember, the power of the lens is determining how light is bent to help you see things more clearly. Hey there! Let's dive into a really interesting concept in physics today: focal length and its impact on light. Imagine you're wearing glasses or looking through a magnifying glass. You've probably noticed how the power of the lens affects how sharply or softly things appear, right? Well, that's exactly what we are talking about today: the focal length. Let's break it down. Focal length is the distance between the lens and the point where light converges or diverges. If the lens has a short focal length, it's powerful, meaning it bends light more sharply. On the other hand, if it has a long focal length, the lens has low power and the light bends more gradually. Think of it this way: a magnifying glass with a short focal length makes objects appear more sharply focused, while a camera lens with a longer focal length gives you a zoomed out effect. Light takes longer to focus. Now, let's check out this formula. The power of a lens, P, is related to its focal length, F, with the equation power P equals 1 divided by focal length, F, where F is in meters. For example, if the focal length of a lens is 0.5 meters, the power of the lens is 2 diopters. You get that by substituting 0.5 into the equation, and boom! Power equals to diopters. Just like when you need to correct your vision, knowing the focal length helps in designing the perfect lens for your needs. Pretty cool, right? Now, let's dive into the real-life applications of lens power and see how physics helps us in so many practical ways. First up, eyeglasses. For people with vision problems like short-sightedness, myopia, or farsightedness, hypermetropia, lenses with high power are used to correct their vision. For example, a person who has difficulty seeing distant objects clearly may need a positive lens to bring things into focus. Ever wondered how cameras zoom in and out? Well, they do so by adjusting the lens power. Lenses with varying powers help cameras focus on objects both near and far, just like a pair of glasses, but for capturing the perfect shot. Next, we have microscopes and telescopes. Lenses with different powers are essential here as well. These instruments use lenses to magnify tiny objects or bring distant stars and galaxies into clearer view. Here's a quick example. Let's say you have a lens with a power of +3 diopters, D. This lens can help correct nearsightedness, allowing a person to see distant objects more clearly. It works by focusing the light properly onto the retina. And finally, let's look at the formula that explains lens power. P equals 1 divided by F, where P is the power of the lens and F is its focal length in meters. For a lens with a power of 3 diopters, we know that P equals 3D. Hello everyone. Let's shift our focus now from convex lenses to concave lenses. You may have seen these in spectacles used by people with myopia or nearsightedness. The lenses look slightly hollow at the center and thicker at the edges. That shape gives them very different behavior compared to convex lenses. A concave lens always produces a diminished, upright, and virtual image of any object placed in front of it. No matter how close or far you put the object, the image is always smaller and appears on the same side as the object. This is why we say the magnification for a concave lens is negative and always less than 1. Mathematically, m is less than 1. That means the image height is smaller than the object height. Unlike convex lenses, concave lenses can never give you a real image on a screen. As you can see in the ray diagram, when parallel rays pass through a concave lens, they spread out or diverge. If you trace these rays backward, they appear to meet at a virtual point behind the lens. That's where the smaller, virtual image is formed. In real life, this principle is incredibly useful. Concave lenses are fitted into glasses to correct myopia. They make distant objects appear smaller but clear, allowing the person to see them properly. So, remember this simple difference: convex lenses can magnify and even form real images, but concave lenses always shrink the image, giving a virtual, upright, and diminished version of the object. Hello, everyone. Let's dive into an exciting application of lens formulas, and I promise by the end of this, you'll feel like a pro at solving these problems. Imagine this: you place an object 20 centimeters away from a lens that has a focal length of 10 centimeters. Now, the task is to find the image position and magnification. Simple, right? Let's break it down step by step. We start with the lens formula: 1 divided by f equals 1 divided by v minus 1 divided by u, where f is the focal length of the lens, v is the image distance, u is the object distance. Here, f equals 10 centimeters and the object distance u equals negative 20 centimeters. So, we need to solve for v, the image distance. Now, after plugging in the values and solving for v, we find that the image distance is 20 centimeters. Look at that. We've solved for it. Now let's move to magnification. Magnification, m, is given by the formula m equals v divided by u. So, we plug in the values for v and u. M equals 20 divided by negative 20. And voila! The magnification comes out to 1. That means the image is the same size as the object. Pretty cool, huh? And if you look at the diagram, you can see this visually: the object, the focal points, and the image are all in perfect balance. The image is formed 20 centimeters away from the lens, and because the magnification is 1, it's of the same size as the object. To wrap it up, the image distance is 20 centimeters. The magnification is 1, meaning the object and the image are of equal size. And that's how we can easily use the lens formula to solve such problems. Hello, students. Let's wrap up today's lesson on the power of a lens. Have you ever wondered why glasses help us see better or how cameras focus on objects? Well, it all boils down to the power of the lens. And guess what? The concept of lens power is linked to something called focal length. Now, imagine using a magnifying glass to burn a piece of paper that's focusing light with a lens. The power of a lens is essential for understanding how lenses bend or refract light. It's crucial in many applications like eyeglasses, cameras, and even telescopes. Without understanding lens power, we wouldn't be able to fine-tune these devices to give us clear images. The lens formula is your best friend when solving problems related to image formation. It connects focal length, image distance, and object distance. And don't worry, we've got an easy formula to help us out. Here's the formula you need: P equals 1 divided by F, where P is the power of the lens in diopters and F is the focal length in meters. The shorter the focal length, the greater the power of the lens. So, to summarize, by understanding lens power, we get to control how lenses focus light, which is a game changer in everything from vision correction to high-powered telescopes. I hope you're feeling more confident about lenses now. Keep practicing and see you in the next lesson, where we'll explore more cool physics concepts.